SwayamPrabha. Digital India. Educated India.
Hello, welcome back. We are going through the energy and energy analysis, and this is the second part of the lecture of that series, of that particular topic. So what we have done until now within this topic is to understand the concept of energy and different forms, nature of internal energy, the concept of heat, and the terminology associated with energy transfer by heat. In this lecture we are going to look at work and work related aspects, that is different kind of works. So work like heat is an interaction at the boundary between the system and the surrounding. If you consider a closed system, and if there is energy transfer is there, and if it is not due to the heat, then it has to be due to the work. So energy transfer due to the heat is due to the difference in the temperature. So if there is no temperature difference and if there is energy transfer, it has to be due to the work, and that's what we talk. So you have this heat and work for a closed system, and if there is no temperature difference, then energy transfer has to be due to work. Now work is the energy transfer associated with a force acting through a distance, and so the examples are the rising piston, rotating shaft, and electrical wire crossing the system boundary. These are all different kind of work, and this is related to some form of force which acts to a distance. The unit is same as that of heat, that is kilojoules, and the typical work during a process between 1 and 2 is referred to as W12. So it is not referred as delta W, and we will discuss this part in subsequent slide. We'll simply refer the work between the process between the state 1 and 2 as simply W. The work done per unit mass is given by the simple division of W with mass, and will be written as small w. Okay, and the work done per unit time is nothing but power. So the work or heat has a direction, and we need to provide the magnitude as well as direction to provide complete description. So this is, we are going to discuss now a formal sign of convention. So heat transfer to the system or to a system is positive, and work done on a system is negative. Or in other words, we can write in this form that we are going to define this Q in, Q out, W in, W out. Specific directions is already provided here. So if you are not aware of the direction, you can assume a direction and you can do the calculation. If the value is positive, that means your assumptions are right. Otherwise, you have to change the direction. Now, heat and work both have similarities. The both are recognized at the boundary of the system as they cross the boundaries. That is, both heat and water are boundary phenomena. Okay, this we have emphasized now many times. System possesses energy, but it does not contain heat or work. Both are associated with a process, not a state. Okay, and unlike properties, which is a point function, heat or work has no meaning at a state. It's only relevant when there is a change in the heat or change in the states. Both are path function. That's something which we are going to discuss a bit now. Okay, so essentially means that both work and heat are path functions. Their magnitude depends on the path followed during a process as well as at the end state. It's not only the process, but as well as the end state, they depend on it. Okay, so let us further look into this. Let's take a case where you have a change in the volume as you change the pressure. There are two processes which are considered here. This is a PV diagram. You have a state 1 and state 2. You're changing the volume from 2 meter cube to 5 meter cube. Now, considering the volume itself is a state property or is at the point function, thus for both the process, your delta V will remain same. Since properties are point function, they have exact differential. That means the integration of dV is simply delta V. But that is not true for work. For work, you have different values can be seen for different processes, because they depend on the path. So the path functions, as we have already discussed, they have inexact differential. So if you integrate the work along a path, it should not be delta W. It should be written in the form of, let's say, W12. And the reason being that delta W means that you are saying the system contains work, but this is not true. The system do not contain. As we already discussed, that the work is recognized only at the boundary, thus we cannot write the integral of delta W in the form of delta W. So in order to avoid all this confusion, you can simply write any change as simply delta W1 to 2, or you can write as process A or process B as depicted in this particular example. Okay, so there are many forms of work. There are mechanical forms and there are non-mechanical forms. So let me first describe the mechanical forms of work. The two requirements for a work interaction between a system and surrounding. There must be a force which acts on a boundary, and the boundary must move. So this is an example where the force is constant, where in that case you are just going to use the expression force into distance. When force is not constant, then you can integrate F over ds from point 1 to point 2, as in this case. Okay. So the work done is proportional to the force applied and the distance traveled. If you are not doing any movement, as in the case of this gentleman sleeping on the bed, then there is no work done for the particular time frame. So there are other forms of work. One is shaft work, which is extremely relevant for many engineering applications, such as boat, where the energy is transferred through the rotating shaft. Okay, so let's consider the shaft here, the rotating shaft here, where you are applying a force on a moment of arm R. So in that case you generate torque, and the torque is given by T equal to F multiplied by R, which essentially means that F is nothing but T divided by R. And the distance you also can calculate by knowing the number of rotation done. So for example, for case of n number of rotation, the total distance which the force has acted on it is the circumference multiplied by n. So the work shaft work would be simply F multiplied by S. In that case you can replace this expression by these values, and in such case you can get this expression, which is 2 pi n multiplied by the torque. Okay, so in case of per unit expression, this will be the power transmitted through the shaft will be given by this expression, where the rate of rotation is considered. So it is proportional to the torque as well as the number of rotation per unit time. There are other forms of work, mechanical work, such as spring. Okay, here for example the spring is resting, and then when you apply a force, the displacement caused can be given as dx, then the work would be given in this form, where simply you multiply F and the displacement. Now this force, if it is a linear elastic spring, we know that this force is proportional to the displacement, and hence F is equal to kx can be replaced here, and you can integrate it in order to get the work of spring for two positions x1 and x2. But you can also analyze the work done on an elastic solid bar, which can be considered an elastic spring, and you can apply a force, and force should be in the elastic regime, where the force should not be so large that it distort the solid bar permanently. In such case you can express the work of elastic done on the solid bar in this form, where this is a normal stress. The other example of mechanical form is surface tension work. So now this is a rigid wire frame which contains the film. This is simply, let's say, a water film. Now the air is outside, so there are two interfaces. So there are two water air interface. Okay, as we know, surface tension acts on the interface. So you have two lines of interfaces, which essentially is associated here. So what is the force which is required to overcome the macroscopic force between air and water? That will be the force, that will be the surface tension multiplied by the interfacial length here. Okay, so in this case the interfacial length is 2b. So this is the surface tension, this 2b is the interfacial length, which essentially is nothing but the length of this wire here. This is B, and the other side of it. So that becomes B plus B is equal to 2B. Okay. So you can calculate the force, calculate the work done completely when you change from this position to this position. That means from 1 to 2 by this expression here, where this surface tension and this is the area which you are changing, which is nothing but 2B multiplied by the displacement which you are causing by moving the wire, okay, from position 1 to position 2. Okay, so the other form of work could be, you can take an example of, let's say, elevator car, and here you know that the body is raised, as you use in an elevator or lift. In such case, there is no temperature difference. Thus, the work done should be, thus the whole change in energy is due to the work done by the elevator. So in such case, the work transfer needed to raise a body is equal to the potential energy of the body, or if you want to accelerate a body, that the work transfer would be equivalent to the change in the kinetic energy of the body. Okay, there are other non-mechanical work such as electrical polarizable work, which we are not going to discuss in details. So that will be the end of this lecture. We are going to introduce the first law of thermodynamics and other aspects of that in the next lecture.